Okay, let's start with chapter 12, section 5. This is called torque. If we apply a force to a point on an object which is not the center of mass of the object would tend to experience a rotation. And so the ability of the force to cause a rotation depends on three factors, and I'll list those shortly. The three factors are the magnitude of the force, the distance of the lever arm, and we call that lever arm R, from the point of application of the force. And the third factor is the angle at which the force is applied. When these conditions are satisfied, we have what is called a torque acting on the object. The symbol for torque is the letter tau, which is a Greek letter, and we define this quantity torque as follows. So the torque is equal to the lever arm multiplied by the force times the sine of the angle between the lever arm and the force. So we can say that the angle phi, this letter is called phi, is the angle between the lever arm and the force. And the torque tau is at a direction which is perpendicular to the plane of the lever arm R and the force F. Also note that the lever arm R and the force F are both vectors. So we can say that if we note that R and F are both vectors, then we can write that the torque is equal to the cross product of R and F, or the vector product of R and F. This is called the vector product or cross product. We can illustrate this as follows. Let's suppose that we have a wrench that is used to turn a nut or a bolt. So we consider a wrench turning a bolt, and so we can say that, let's say we have the wrench this way, and this is the bolt, of course, and so we can identify a force. Let's say this force acts vertically downwards, F, and the distance from the force to the axis of rotation is the distance R, which is called the lever arm, and the axis of rotation is this axis here. So in this exercise, or in this example, the angle is 90 degrees. You can think of the angle as 90 degrees here also. And so in this scenario, the torque is given by R cross F, which is equal to RF times the sine of the angle 90 degrees, which is equal to R times F. So in this case, the torque is a maximum. Let's consider another scenario like that, where again we have our bolt and we have that. And let's say that this time the force is at a certain angle. Let's say this is F, and again this is your lever arm R, that way, and the angle between the force and the lever arm is this angle phi. So this time the torque is equal to R cross F again, and this can be written as RF sine phi. So we can look at two interpretations of the torque. We shall start off by using our example above in the second case. So let us consider again the wrench turning a bolt. We shall do this to arrive at two interpretations of torque. So let's consider again, this is our wrench this time, and let's say that the wrench is this way and this is the bolt here. So let's apply a force this way. So this is your force F, and your lever arm is R, and the angle is phi this way. So we can calculate the torque first by taking a vertical component of the force. This would be F sine phi, and then this is a horizontal component, F cosine phi. So the torque is equal to R times F sine phi. So this is basically saying that the torque is equal to the lever arm R multiplied by the perpendicular component of the force, F perpendicular, where F perpendicular is equal to F sine phi. Then we can do the same thing to get a different interpretation. Let's suppose we have the same wrench again, our same setup, and again we have our wrench. So let me redraw that, and this time again we have our force F. This is our lever arm R. I'll draw it here this time. Lever arm is R, and this is the angle phi between the two. This time let's take the force going down that way. So the line of action of the force is this line here. So this is called line of action of the force. So now we can take a line from the lever arm here. Let's call this R perpendicular. So this angle is 90 degrees. So this is the perpendicular distance from the lever arm to the line of action of the force. So R perpendicular is the distance, or the perpendicular distance from lever arm to the line of action of the force. So the torque can be calculated again. Torque is equal to R cross F, as we know, and that can be written as R sine phi. Actually, before we do that, torque is equal to R cross F. And then from our diagram, let's redraw the diagram here and redo it. So we have that this way. Our force is F, this angle is phi, and we've drawn the line of action that way. So this is perpendicular to that. So this is R perpendicular, and this is your lever arm R. So this angle is also phi, and so we can say that sine phi is equal to R perpendicular divided by R. So that when we calculate torque, torque is equal to R cross F, and that can be written as R sine phi. So essentially what we are saying here is that the torque can be written as the perpendicular component of the lever arm to the line of action of the force multiplied by F. So we've given two interpretations of torque. One where we take the perpendicular component of the force multiplied by the lever arm, and the second one is where we take the perpendicular distance from the lever arm to the line of action of the torque. Okay, so this is second interpretation, and the first interpretation was R times F perpendicular. Those two are exactly equivalent. So let me spell this correctly. So we've got our definitions of torque and how to interpret the torque. So we can go on from there now. So let's look at some examples of torque, and then we'll talk about net torque. First of all, let's get a convention for torque. So let's define a convention for our usage of torque. We can do that by looking at the example below. So let's first draw a bar like that. So let's say we have a bar that way, and we have two forces acting on it. So let's say this is the axis here, and we put one force here. This is a force F1 at a distance R1 from the axis, and we have a distance R2 and a force F2. Both of these forces will exert torques on the bar. So we can say that torque 1 is given by T1, like a tau 1 like that, and it's equal to R1 cross F1, which is equal to R1 F1 sine 90, and that can be written as R1 F1. So the first torque is R1 F1. Notice that by convention F1 is negative and R1 is or positive. So we can say that by convention F1 points down, so it's negative, and R1 is on the positive side. So T1 is a negative torque. So we can write torque 1 to be equal to minus R1 F1, because F1 is negative and R1 is positive. Then for torque 2, the force is again negative, so it's going to be the force is negative, and the distance is R1 is also on the negative side, so we shall have minus R2, and minus F2. So this torque is positive. So torque 2 is a positive torque. So we can identify two torque directions. Let's identify the torque that tends to cause a counterclockwise rotation, or in this case, the torque that tends to cause a clockwise rotation as the negative torque, and in this case, that negative torque is torque 1, so it's negative. So torque 1 is the clockwise torque. CW means clockwise. And then we shall say torque 2 is a positive torque, and we shall identify that as the counterclockwise torque. So we can say torque 2 is counterclockwise, like that. So we can say that torque 1, which is equal to minus R1, F1 is the clockwise torque, and torque 2, which is equal to R2, F2 is counterclockwise. Okay, so those are the conventions we shall use. The clockwise torque is negative and counterclockwise torque is positive. Let's try an example. Find the net torque in the examples or in the figures below. So first one, we have an axis here, and this is the lever arm. Let's call it R1, and let's put a force F1. So R1 is 10 centimeters. F1 is, let's say, 20 newtons, and it's negative because it's pointing down. And then number 2, we'll put an axis somewhere in here, and we'll put a force F1, a force F2. Let's take this to be 10 newtons, 15 newtons. Both of these are on the negative side. And then we're going to have, this is R2 and R1. This is 15 centimeters, and this will be minus 10 centimeters. So let's write R2 equals minus 10 centimeters. R1 is 15 centimeters, just to be clear. And then the third exercise we can do, number 3, let's take this again. This is our axis. Then we can put one force here. Let's call this F1. Distance R1, 15 centimeters, F1, 10 newtons, negative 10 of course. And then we can put another force here, F2, let's do 8 newtons, and R2, minus 5 centimeters. So this is your axis again. So we can look at some solutions. In the first exercise, the net torque is just equal to torque due to force 1, which is equal to R1 times F1 with a negative in front of it. So we multiply the lever arm R1 with the force F1. Lever arm is changed from 10 centimeters to meters, so it's 0.1 meters. Let's put a negative here, multiplied by the force F1, which is 20 newtons. And so this gives us a net torque of minus 2 Newton meters. Number 2, we have our torques. The net torque is the sum of the clockwise torques and the counterclockwise torques. So we have two torques present, clockwise and counterclockwise. So in the first clockwise torque, we have torque 1, which is torque 1 plus torque 2. So torque 1 is minus R1, or it's R1 times F1. Put the negative signs in later. And torque 2 is R2, F2. So the first torque is going to be 15 centimeters multiplied by minus 15 newtons. So it's going to be 0.15 times 15. Put a negative in front of it. And the second one is going to be R2, which is 10 centimeters, and F2, which is 10 newtons with negatives in front of them. So this would be negative 0.1 meters times negative 10 newtons, that way, from those two forces. So we shall have negative 2.25 Newton meters plus 1 Newton meters. So this can be written as negative 1.25 Newton meters. So this gives us the net torque on this object. So because we have a larger clockwise torque than a counterclockwise torque, the object is going to rotate in the clockwise direction due to the presence of the two of the torques on it. So the clockwise torque is larger than the counterclockwise, so it rotates clockwise, which is the negative torque that we just found. In the third example there, we can do it again. In the third exercise, the net torque again is the sum of the two torques. So the net torque is the sum of the torque 1 plus torque 2. And if you look at this exercise here, because torque 2 points upwards, it will tend to give it also a clockwise rotation. Torque 1 points downwards, so that gives it a clockwise rotation. So both torques are clockwise torques, if you take a look at it carefully. So what we have is in torque 1, we're going to have again the lever arm, which is 15 centimeters, change that to meters and multiply by the force. So we're going to have 0.15 with the negative in front of it times 10 newtons. So that will be Newton meters plus the other torque, which is due to force F2 and lever arm R2. So minus 5 centimeters times F2, which is pointing up. So that's a positive. So we shall have minus 0.05 meters multiplied by 8 newtons. So the net torque can be found this way. This is minus 1.5 Newton meters minus 0.4 Newton meters. So that will give us negative 1.9. Again, the negative sign just tells us that it's a clockwise torque because the net torque is negative, so the object will tend to rotate in a clockwise direction. So let's look then at a general rule for the sum of all torques on an object. So we'll say just add in multiple torques. So suppose we have an object with multiple forces acting on it at different lever arms. We can find the net torque as follows. So let's take an object of arbitrary shape like that, and let's say that it has an axis like that, so it's going to rotate about that axis. We can put multiple forces on this object in different directions. Let's call this F1, let's call that F2, let's call this Fn, and we can say they are all at different distances. This is R1, this is R2, and this is R3. So the net torque on this object is the sum of all torques. So this will be due to torque 1 plus torque 2 plus torque n. And so the net torque is just the sum of all the torques like that. Again, you keep in mind that torques are vectors, so you just put the vector notation on them all that way. So this is the end of the section on torques. We shall go into the section of rotational dynamics next.